All right, guys, we're on to our last section. We again skipped 6.5 and we're going on to 6.6, which is converting normal to binomial. So it's a normal curve, and now we're going to make it binomial, which is from the last chapter. So a brief review. Remember the 4 requirements for binomial was the funny acronym BINS. So really quickly, B stands for binary. So there's a success versus a failure. The I is going to be each child is independent. Is independent of each other, which I'm just going to write independent. The N is going to be fixed number of trials. And S is going to be the probability of success. Again, that's from the last chapter. So some notations again from the last chapter is N is going to be number of trials. P is probability of success. And Q is going to be probability of failure. And then X is going to be the number of specific trials. Again, I just wanted to cover some review questions from or parts from the last section. Okay, so to convert from something that's normal as approximation to binomial. Okay, so the first thing you want to do is you're going to actually have to check all 4 requirements. Now, I'm going to ask you check all 4 requirements. When I do, that's when I ask it. But usually this is don't have to do this. Don't have to do this. Just keep in mind. Okay, unless I ask for it, usually you just have does it fit all these qualities? Okay, the second one you do actually have to check, and I'm going to start. This one you do have to check, and it's going to be N times the probability has to be greater or equal to 5. And when I say and, that means both of these have to be true. N times Q has to be greater or equal to 5. Okay, this one you have to check both. Okay, not just one or the other, both of them. Okay, and they both have to be true. Okay, so if all requirements are met, then, and if you remember back in the chapter, do you guys remember what your mu was? What the formula was? The formula was N times P. And what was your sigma? That was the square root of N times P times Q. I actually don't care about my variance. It's just more of those two. Okay. So here are the steps. So the top was the requirements. Here are the 4 steps that you do. Okay, so the first one is check the requirements. Again, the 4 in your head, and then you're going to check that NP is greater or equal to 5, and NQ is greater or equal to 5. Again, that's the first thing you're going to do. The second step is you're going to actually calculate mu, which is N times P, and sigma, which is the square root of N times P times Q. Okay, the third thing is going to say, you're going to look at the chart on page 8. Now, I took this from your book. I'm writing this out, but it says look at chart, essentially what you're going to do for wording. Now, I didn't put every single word that stands out to this, but most of the words stand out. And the last thing is the thing that we've been doing all chapter long is there's a 3-part to it. So the first part is sketch. Then the next part is write out problem. And then the third part is use normal CDF. Again, same thing as before, except now it's a part within an entire problem. Okay, so we're gonna go ahead and we're gonna try our first example. But before you do that, we're gonna go ahead and do the wording of the chart. Actually, we'll do the wording of the chart as we go through the first example because they're on the same page. Okay, so we're gonna go ahead and do this. So example 1, in one of Mendel's famous hybridization experiments, he expected that among 580 offspring peas, 145 of them would be yellow. But he actually got 152 yellow peas. Assuming that Mendel's rate of 25% is correct, find the probability of getting 152 or more yellow peas by random chance. That is, given n is equal to 580, so you're given your n, and p is 0.25, find the probability of at least 152 yellow peas. Is 152 yellow peas significantly high? Okay, so this is like the main part. So we're gonna call this A, and then this part is it high, which is probably B. Now notice I didn't go over high and low. It's the same formula as before, but we'll worry about that later. Okay, so I'm gonna go ahead and write, okay, so we have our N, we have our P. Now if our P is 0.25, how do I find my Q? That's 1 minus 0.25, which is 0.75. Okay, so we're gonna go ahead and we're gonna do all the 4 steps, and then that's just for part A. So the first step is to check that NP is greater or equal to 5. So the way I do this is I write NP equals, and our N was 580, and our P is 0.25. And I'm gonna go ahead and calculate that, which I did on my calculator already, which is 145. And I wanna show that it's greater or equal to 5. Okay, and then we have to check out NQ because you have to do for both of them. So NQ, which is 580 times 0.75. Okay, and you're going to use your calculator, and I got 435, which is greater or equal to 5. Cool. Step 1, done. They're both equal to 5. I can keep going. Now, if they're not equal to 5, then like technically you can keep going and just say it's not reliable. But again, we don't worry about that until the next chapter. Okay, so step 2, if you look at your notes, you want to find your mu, which is n times p, which is 580 times 0.25. And guess what? It's the same as this top part, which is 145. Okay, and then you want to find sigma, which is the square root of n times p times q, which is 580 times 0.75 times 0.25, or 0.25 times 0.75. And then how many decimal places do you want to round to? That's right, 3. Okay. Our third step is to go ahead and find, using the wording. So we're going to find the probability of at least 152. So I'm going to actually go to the bottom part of this, and we're going to go ahead and go through this bottom part. So if you want to make a note, I went from here to here, and then we're going to go ahead and do the bottom part, and then I'll go back to the example. So it says when we use the normal distribution, which is continuous. Remember, continuous means that it's every single continuous. I'm spelling it wrong. Continuous. Okay. As an approximation to the binomial, which is discrete. So remember, you guys had this question on your homework for the last chapter. Is it discrete or is it continuous? So normal distributions are continuous because it's the area under the curve, while binomial is success and failure, and it has to be countable. So what essentially we're doing is we're converting one into the other. So a continuity correction is made to a discrete whole number. So we actually have to change the discrete whole number in the binomial representing the discrete whole number x by the interval of either x minus 0.5 or x plus 0.5. Okay, and that is adding 0.5 or subtracting 0.5. And again, that's why I gave you guys like this wording chart. Again, I took this from your book if you want to. So I took from book. Okay, so this is for example 1. So I just did the wording based off this, but it works out for every single one. So when this said statement about discrete, so this is binomial, we're going to go ahead and find continuous. Oh, I'm spelling it wrong. Continuous, which is going to be normal. I guess I already wrote normal. Okay, so when I say at least 152, so is that including or not including? Well, that's 152 and above, and I want to make sure I include 152. So if I want to include 152, and every single time, if you remember, it's always greater than 152. Well, greater than doesn't mean I include it. So how do I show that it includes it? Well, I can't use greater than or equal to. So instead, I'm going to subtract a 0.5. So it's essentially the probability of x is greater than 151.5. And why did I do 151.5? Is because I want to make sure I include 152. And if I get a number that's greater than 151.5, I'm including 152. So I'm going to say this is to the right of 151.5. Okay, so when I say more than 152, more than does not include 152. So we're going to do the probability of x is greater than 152.5. Okay, so we don't want to include 152, so this is going to be to the right of 152.5. At most, now again, I didn't do all of the words, but I tried to do as best as I could. At most 152, that means we include 152 and below. Okay, so probability of x is less than, and if I want to include 152 and below, I'm not going to do 151.5 and less, I'm going to do 152.5 and less. And this is going to be to the left of 152.5. And the last one, fewer than 152, again, doesn't include 152, so that's going to be probability of x is less than 151.5, which is to the left of 151.5. Okay, so just think about it in terms of like, okay, do I want to include it, do I not? And if I don't want to include it, what number do I use? If I do want to include it, what number do I have to go for? So it's like an overestimation or an underestimation. And if you want to do exactly 152, okay, we're going to do the probability of 151.5, which is less than x, which is less than 152.5. So essentially, it's going to be, notice 152 is in there. Okay, so this is going to be between 151.5 and 152.5. Again, this is just an example I used for all of them, for just this example. Okay, so this is the wording chart. So if you want to look at it, if you want to label this wording chart, you can. And again, I got this from your book. So part 3, we're going to solve, we're going to look at the wording chart and figure out what they're talking about. So the probability of at least 152 yellow peas. Okay, and I'm going to rewrite this using one of these. So at least is right here, and it's going to be at least 152. So if it's including 152, this is the same as the probability of x is greater than 151.5. Okay, now step 3 and step 4 are the same. Step 3 was just look at the chart. Step 4 is to actually do it. So I'm going to call this step 3 and step 4. So I already wrote out the problem. I'm going to go ahead and draw the sketch. So the sketch is going to be 152, which is greater than my mean. So my mean was 145, so it's over here. And at least it's more, so I'm going to go ahead and shade this in. Now what do I label the bottom? Well, I'm not going to label it 152, I'm going to label it 151.5. Okay, why? Because that's what the problem says. Okay, so I'm going to go ahead and write out the normal CDF. And at least 152. So again, what makes this different from before is I'm giving you a proportion this time. And so it's not 152 to 1,000 and then your mean or standard deviation. We're converting this to a binomial. Okay, so our lower is not 152, it's 151.5. Our upper is still 1,000. Our mean is n times p, so I'm going to write 580 times 0.25. Again, you can just write out the 145, but it's mostly sigma that I care about. So you're going to write sigma as 580 times 0.75 times 0.25. And I'm going to go ahead and label this. So this is your lower, this is your upper, this is your mean, and this is your sigma. Okay, and I'm going to go ahead and use my calculator, and I'm going to round to how many decimal places? 3. So 151.5. 1,000, our mean was 580 times 0.25, and I just have to type that in there, it's kind of nice, times the square root of 580 times 0.25 times 0.75. And I got my answer to be 0.267. Now that was the answer to A. So find the probability of at least 152 yellow peas. Done. Okay, so that was all for A. B. Is 152 yellow peas significantly high? So if you remember, significantly high was mean plus 2 standard deviations. Okay, guess what? We already found our mean and our standard deviations. Our mean was 145, and our standard deviation was 10.428. So 2 times 10.428. I'm going to calculate that to 165.856. I already did it before. So this is my number. Now I'm asking, is 152 greater than this? The answer is no. So I'm going to write, since 152 is not above 165.856, it is not significantly high. And that's it. All right, we got one more example, and then that's the end of our notes. Okay, so our last one, you have all of the space. This bottom part, I didn't have more notes, so if you need to write bigger, you can. So it says example 2. Using example 1, so same part, finding the probability of exactly, so this time we're changing it to exactly 152 yellow peas among the 580 offspring peas. That is, given 580, assuming that p is 0.25, find the probability of exactly 152 yellow peas. Is this result useful for determining whether 152 yellow peas is significantly high? Again, we're asked to find parts. We're asked to find this one, and we're asked to find this one. Okay, now I don't have to do all of the steps over again because this would just be the same idea. So I'm just gonna go straight into drawing out exactly 152 yellow peas. Now, if you look at your wording chart, now I don't have my wording chart in front of me, but look for exactly. Exactly is the last one. Okay, so I'm gonna write it out first. So the probability of exactly 152 yellow peas. Now, if you look at the wording chart, that's going to be 151.5 is less than x, which is less than 152.5. And that's essentially how I got that. So the next thing I'm going to do is I'm going to sketch it. And 151.5 is here, and 152.5 is here. And I'm going to go ahead and sketch this and shade it in. So that's essentially what we're trying to find. So what's my last step is to use normal CDF. So if I use normal CDF, I'm going to have my lower to be 151.5, my upper to be 152.5. My mean, if you remember, is 580 times 0.25. And my standard deviation was the square root of 580 times 0.75 times 0.25, all in a big square root. And then I want to label it. So this is lower, upper, my mean, and my sigma. I'm going to use my calculator one last time. So second bars, normal CDF, 151.5 is already there, 152.5, and then if you save it, it's actually the same number, so I don't have to retype everything in. And I get 0.031. And that is my answer. Then, so this is all of part A. Again, I didn't have to do every single step because I already did it for the front. It's just using it. Now, if this was something else, then I would have to check out all the requirements. So like if is it greater than or equal to 5 for n times p and n times q, and everything else. Okay, so part B says, is this result useful for determining if 152 yellow peas is significantly high? Yes, it does. If the number is less than 5%, remember that rule? It's significantly high or low. Sorry, if it's greater than. Okay, so in this case, I'm going to write this out. So I'm going to say since 0.031, which if you convert this to a percentage is 3.1%, is less than 5%, it's not very likely to happen. Think about it. You have a 3.1% chance of it happening. Is it likely to happen? No. And so it's not significantly high or significantly low. If you remember back from the last chapter. Again, we do a lot more of this data analysis later on. It's more like calculating it by hand. Okay, well, that's the end of the notes, so.